The next step of this question is going to be to graph our A of theta in order to determine where our graph will be the largest. So let's go ahead and go to Desmos. So here we are, we're in Desmos. Let's go to the graphing calculator, and we're going to graph our function as 25 sine, I'm going to use x because I don't have a theta button, plus 25 sine x cosine x. That was our function, right? There's an error. Why is there an error? Okay, let's put in some grouping symbols because everybody loves a good grouping symbol, and see if that helps. There we go. So remember, our piece of metal was only 15 inches long, so and we had to break that up into thirds, so it's going to be between 0 and 5. So our maximum height is going to be this first peak right here, which the maximum area, which is going to be 32.47. That 32.47 is our maximum area. So let's head back to our actual PowerPoint. There we go. So next example, we can use the complementary angle So let's talk about complementary angles. Complementary angles are complementary. Two angles are complementary if they add up to 90 degrees. So let's look at this figure, which labels the angles opposite side B to B, angle B, and the one opposite side A to B, angle A. Sine of B is B over C, which is the same as cosine of A. Cosecant of B, therefore, would be the same as secant of A. Cosine of B, which is A over C, is the same as sine of A. Secant of B, which is C over A, is the same as cosecant of A. Tan of B, which is B over A, is the same as cotangent of A. And cotangent of B is the same as the tan of A. This is often referred to as the complementary angle theorem. So because of these relationships, the functions for sine and cosine, tangent and cotangent, and secant and cosecant are often called co-functions of each other. And the identity can be expressed in words as follows. So co-functions of complementary angles are equal. Co-functions of complementary angles are equal. So let's go ahead and solve a couple examples using the complementary angle theorem. So the sine of 79 degrees, that would be the same as the cosine of the complementary angle, so the cosine of 90 degrees minus 79 degrees. So same as the cosine of 11 degrees. For B, which I guess they were going to give me, tan of pi over 18, that's the same as cotangent of pi over 2, which is 90 degrees, right? Minus pi over 18. So I get cotangent of 9 pi over 18 minus pi over 18. That's the same as the cotangent of 8 pi over 18, which is the cotangent of 4 pi over 9. Last but not least, problem C, if I have sine squared of 55 degrees plus sine squared of 35 degrees, well, that's the same as sine squared of 55 degrees plus cosine squared 55 degrees, because 55 and 35 add up to 90 degrees. Well, this is one of our identities. This is just going to equal 1. So we have another theorem that says for the right triangle shown, c squared is a squared plus b squared, so the Pythagorean theorem, and that the two angles A and B have to add up to 90 degrees. And that makes sense, right? Because all the angles of a triangle add up to 180 degrees. So for example 4, let's solve a right triangle. When solving a right triangle, that means finding all of the unknown angles and side lengths. So in this case, I know B is 4 and A is 35. I need to figure out capital B, A, and C. I know that A plus B have to add up to 90 degrees. So 35 plus B is 90 degrees. That means B is 55 degrees. Now, I can use this information to figure out C. I could take sine of B is B over C. So sine of 55 degrees is 4 over C. So C times sine of 55 degrees is 4. C is 4 divided by sine of 55 degrees. Make sure your calculator's in degrees, and you get about 4.88. So C is 4.88. Remember, our hypotenuse is always going to be the longest side, so that's one way to check our work. Next, I'm going to find A. I'm actually going to take the tangent of B, and here's why. This is an approximation. This is not an exact value. So in order to be really precise about my A, I need to only involve what I know. And I know B, and I know the angle B. So tan of B is opposite over adjacent, so B over A. So tan of 55 degrees equals 4 over A. So if I solve for A equals 4 over tan of 55 degrees, which is about 2.8. So now that I've found all of the unknown side lengths and angles, I have solved this triangle. Let's practice solving another one. I have that A is 4, B is 2, and I need to find C, A, and B. Well, tan of B is going to be B over A. So tan of B is 2 over 4. Tan of B is 1/2. So if I take tan inverse of both sides, or arctan, tan inverse of both sides, I get B is 26.6 degrees. So I can use that information to figure out that A plus 26.6 degrees, A is 63.4 degrees. I can also use Pythagorean's theorem to find the length of C. A squared, so I've got 4 squared plus 2 squared equals C squared. 8 plus 4 is C squared. 12 is C. C squared, I take the square root of both sides. I have the square root of 12 is C, which I can simplify to 2 square root of 3. So my side angle is 2 square root of 3. I actually made a mistake because 4 squared is not 8, it is 16. Sorry guys, I'm recording this a little later than I normally do. So I have 16 square root of 20. Square root of 20 can simplify down to 2 square root of 5. So C is 2 square root of 5. But always remember to simplify your radicals. It's really, really important.